Bismillahirrahmanirrahim. Assalamualaikum warahmatullah, and a very good morning. So we now continue with lecture 4 on the normal and tangential coordinate system, or normal and tangential components. So for cases where when the path is known, it is sometimes more convenient to use the normal tangent coordinate system. Okay, so let's see what do we mean by this. Let's say we have a particle moving from origin O, okay, and the path of it started at O and it follows a certain path. So this is the path, and this is the point where the particle is here, P, right? And we can take this in the direction of increasing displacement S. And the unit vector tangent, we find the tangent to the path. So this is tangent, and I use T here. And we identify a unit vector of tangent to be U subscript T, underline. And we find a normal to that, to the tangent, which is the N direction. And we have a unit vector of U underline subscript N. So this is called the unit vector tangent, unit vector tangent, and unit vector normal. So this is the unit vector normal. So from here, because of the origin is located at the particle, so the origin is located here at the particle, origin located at particle, so there is no displacement here. So what we have a definition of V. V, the velocity, can now be represented as the magnitude V and the unit vector tangent. So the direction is in unit vector tangent, and V is the scalar or unit magnitude, the magnitude of velocity. So V is the, can I use a different color here? Like this is the magnitude of velocity. Okay, and where V, the scalar V is equals to S over dt. So that's S here. So S is here, and we can find that the scalar V is ds over dt. So that is one set of equation, and there's another set of equation here. And the acceleration can be given as acceleration can be written as dv over dt, and we will have scalar v dot in the direction of tangent ut plus v u dot t. Okay, now it's not normally done this way, but we have to look what is the meaning of du over dt. So we'll spend some time on du over dt. Yeah, so du over dt is you can derive du unit vector, the differentiation of du over dt, but I'll skip the derivation. I'll just show you the results here. Du t unit vector t over t is theta dot un. Okay, theta dot un is the angular velocity as it goes around the curve, is the angular velocity as it goes around the curve, and that can be represented as v, the magnitude of the velocity, v divided by rho, and the direction is in the normal direction un. Yeah, so that you can now have the acceleration here. Let me clear that a bit. So you can have the acceleration here as the tangential component at ut plus en un, where en, where the normal magnitude acceleration is given by v square over rho. Yeah, so in short, the acceleration vector is given by v dot scalar ut v dot ut plus v square over rho un. So that is the representation of velocity as a function of, in terms of the normal and tangential coordinate system. So that's the basic way of representing the motion in normal and tangential coordinate system. So let's look at one of a particular example. There's another one. So if you have a motion again, just like that, and this is the v, and then this is in the direction of the tangent. This is direction of tangent, sorry. So if you have a curve, let's draw a curve here, and you have a position of interest, and this is your tangential direction, and this is your normal direction, you can see that this curve is having a radius at origin O, since it is an origin O, there's a radius here. Okay, so if I remove this component, and then as I draw this as radius rho with origin O, okay, and at the same time we have the normal component n. Okay, so we have a velocity, and that can be represented as the magnitude v and the unit direction, unit vector tangent, and then we have A in the direction, both component, A in the unit direction of the component, tangential component. So let's call this AT UT, and then AN UN. Okay, where AT is V dot, and then AN is V square over rho. So that's how we define the motion of normal and tangent, and there is a relationship between the rho of the path at any point. We can find if you can represent it in terms of y and x. For example, if you have a coordinate system of y and x, yeah, so rho is equals to 1 plus dy over dx square then this whole thing is to the power of 3 over 2, okay, divided by the d2y dx square. This is also another set of equations that we can use to solve our problem. In the relationship of curvature, this is the relationship of the curvature, and dy dx is the function where we can write where y equals to f as a function of. So we'll do some example, or one example to show this fact. Okay. So let's do one example here. So example, this is example 4.1. Let's say we have a system of motion y against x, and there is a slope here. So there is a slope here that is and is given by a slope is given by y equals x squared over 20. And let's say at a particular point here, see, this is x, and this is y, and this is 10 meter, x equals to 10 meter, and y is 5, so 100 by 5 is 5. Okay, and because it's moving downwards, this guy is moving downwards, so let's say this is your tangent and that's your normal. Okay, and let's call this point A, and that particular moment VA is known. Okay, so many arrows. Let's say this particle is moving at VA. So the question is, that particle A reaches point along a parabolic path, a speed of 6 meters per second. So VA is given 6 meters per second, and it is increasing at 2 meters per second square. Increasing at 2 meters per second square. How would you put this? So this word increasing at 2 meters per second square, we can rewrite that as, How? We can write this as v dot a equals to 2 meter per second squared. So that's how we translate this set of data, into this statement. VA equals to 2 meter per second square. Determine the direction of velocity. So the question asks us determine velocity and magnitude of acceleration and magnitude of acceleration. At this instant, okay, at the instant shown. So that's the question. Determine the velocity. So it's given that VA equals to 6 meter per second. So we have all the data. So let me quote you the data. This is the first data. This is the second data. What else do we have? What we don't know is where is the anti-direction. But we have a case where y is given as a function of x. So we know that y equals to x squared over 20. So dy over dx equals to 2x over 20. So it's equals to x over 10. And d2y over dx squared is equals to 1 over 10. So these are the sets of data that we can use. So we have this, we have that, and we have the third box. Yeah. So we know that we can now use that to find rho. So what is rho? We know that rho equals to 1 plus dy over dx square over d2y dx this is to the power 3 over 2. So you can now put that as 1 plus x over 10 over 2. Then this is 1 over 10. What is the value of x? We know that x equals to 10. And therefore we can get the answer here. Rho equals to 28.28 meters. What are we going to do with this rho? So from here, we can now determine few things. We know that we need to find the direction also determine the direction of the velocity. So direction of velocity is tangent to the path. So what is the value there? So dy dx equals to 2 is x over 10 at x equals to 10 dy dx equals to 1. So at A, when we use this value, so that's equal to 1. So or 1 is gradient 1 to 1 is equals to 45 degrees. Yeah. So y equals to 1, x equals to 1, theta is equals to 5 degrees. So then we can link this to our data here. So this particular velocity, the velocity is 45 degrees. So we can draw the direction of velocity to be, if I were to draw the direction of velocity, is VA 6 meter per second. The sudut there is 45 degrees. So that's the answer for number 1. And what would be the magnitude of acceleration? So I'm gonna rub this off. Just need some space to do the calculation here. Let's find the calculation. So what is the direction of acceleration? So I have the solution as the acceleration of A equals to v dot ut plus v square over rho un. Yeah. So do you know where your v dot is? Yes. You know your v dot is already here. So I put this box here. That's your v dot. Do you know your v square? Yes, your v square is here. Do you know your rho? Yes, you know your rho is here. So the answer is answer is 2 ut plus 6 square over 28.28 un. So you can do the math. So that's the answer for the acceleration of A in the answer. I'm sorry. That will be the answer. Okay, let's do another example. Example 2.2. So let's say a car travels around a circular circuit oh my god, with a radius is 300 meters. Okay, and the car increases its speed. Yeah, so car increases speed at the rate of 7 meter per second square, starting from rest. So when you start from rest, what does it mean? At t equals to 0, v equals to 0. Okay. Determine the time needed for it to reach an acceleration. Determine time to reach acceleration of 8 meter per second square. What is the speed? at this instant. Okay, so we have a car traveling around a track diameter. Then that car starts from rest. So it starts from rest, and then it has velocity start from rest, and it doesn't show you. You just see that the v dot equals to. Okay, so determine time to reach acceleration of 8 meter per second square. So what do we mean by acceleration? So assuming that this acceleration is the magnitude of acceleration, so acceleration is, the magnitude of acceleration is at square, tangential acceleration plus normal acceleration. And we know that the tangential acceleration is at equals to v dot, and this is already given to us at 7 meter per second square. And what is the normal acceleration? An equals to v square over rho. You know what rho is? Rho is given to us 300. We don't know what v is. So, but it started from rest. So we know that v equals 2 and increases. So it started from rest. V naught plus at. I hope you know where this formula comes from. So our initial velocity started from rest, so it's 0. So, and at is the this is v dot t, yeah. So equals to v dot t. So the time for it to reach to, so from here we know from this equation that it wanted to achieve 8 meter per second square. So we put 8 here, square root of, we know what 80 is, 7 square plus an square. So that simple calculation will give you an equals to 8 square minus 7 square would give you a so that's a value that you want to be it's not easy to get that. So we square root both sides, so and then we can square both sides. So you got 8 square equals to 49 an square. So we have an 64 minus 89 square root. 64 minus 89 is 25. So an is 5. So we know that we can now link that together. Betul? No, 64. Sorry, an is at this particular point, no. 89 minus 64 plus 20. Yeah. So we link that together. So we can find that at that particular point the v square equals rho equals to 5. So v square equals to 5 times 300 and then square root. So 1500, and we will have about 1500 34.1 per second. So what is the speed of this instant? The answer is 34.1. meter per second. Well, there's some error here, so I have to remove some values are wrong. So let me remove this value. Yeah, it's not 25. Definitely is 64 minus 49. Yeah, so 64 minus 49. So that is 15. So and then we know an is square root to 15, so that is equals to 3.87. So an is 3.87. Yeah, so then we can find the velocity, what is the speed at this particular instance. So that particular instant is v square equals to 3.87 divided by 300. Okay, and then find the square root of that. So we have, hold on, times 300, and then find the square root of that. 1161. So the answer is 34.07 meter per second. So that is the answer for the speed at that particular instant when the acceleration is 8 meter per second square. So that's the second example. Now we move to the third example. If we have third example, so assuming that this is example 4.3. Example 4.3. So it's about a conveyor, and we started from rest. So particle moving from rest. Particle moving from rest. So if it is moving from rest, what do we know? At t equals to 0, the velocity is equals to 0. And increases in speed such that there is it give us the tangential component of at equals to 0.2 t meter per second square, where t is in seconds. So t is in second. Okay. Usually it is this. Okay. Determine the magnitude of its acceleration when it arrives at point B. So determine acceleration when it arrives at point B. Determine acceleration. I'm going to use short forms here. At when arrive at point B. And arrive at point B at B. So what does it look like? It looks like this. It is a conveyor system with a semicircular path. It started from A. It went through a cases where it transformed. This is 3 meter. From here to here is 3 meter. And it will go a conveyor with row of 2 meter. It will go through, and then at point B, there's a point B here. So the question asks us, at point B there is a normal component and a tangential component. So it started from T, from A. It gives us the tangential acceleration 0.2 t, and determine acceleration when it arrives at point B. Okay, so now we need to do some form of integration of what we will find on B. So how would you solve that? So what is our strategy here? So okay, we have to assume that position of B is forming an angle. So let me put the angle here. From this horizontal line to here, the angle is 90 degrees, or that will be pi over 2 radian. So that you know exactly where B is in relation to the horizontal axis. So coming back to this question, we need to find at point B what is the acceleration when it arrives at point B. So that's, we'll say that what is, when it arrives at B, the acceleration at point B is equals to the tangential component of at point B plus the normal component at point B. So an un. And we know that at at is equals to v dot t, and this is given as 0.2 t. It's given, yeah, because it's there, so it's given. And en equals to v square over rho. Rho is given because we know that rho is 2 meter. This one v is not known, so that this is one of the parameter that we need to find. But v is related to at. So we know there is a relationship here. So it started from 0, so that we can use this equation. So at equals to dv over dt. Yeah, so that when we integrate, at is given, so 0.2 t dt, dt, that off, is dt from 0 to t, we can find the speed at v, dv. So we will have v equals to 0.2 t square over 2, so it's equal to 0.1 t square. So from there we know the distance traveled from A to B. So this is distance traveled from A to B. So from A is 3 meters plus pi over 2 radian. So 2 pi r is the r is, so 2 pi r is the whole, so it's a quarter of a circle, so 1/4 of 2 pi r. R is known as 2 meter, so 2 meter. This is from 2 pi r, yeah, so I'm using that as just in case you're not aware of that. So that is the distance. I'm using this orange color. From here to here is 2 meters, and then from here to here is a quarter of that, 2 pi r. So a quarter of 2 pi 2 is, this is equals to 6.5 142 meter. So this is equals to 142 meter. And we know that, so we can use this data as this is equals to S, and we can use that V equals to ds over dt. We can integrate now. So we know that we integrate ds from 0 to 6.142 up to point B equals to the time taken for it to reach B, so 0 to TB, V dt. Okay, so that's equivalent to the integration of 0 to time B. V, we know what V is it is 0.1 t square, so I'm gonna block this. So I'm gonna use that, so 0.1 t square dt. Yeah, so from that you can get 6.142 equals to 0.1 divided by 3, so equals to 0.1 divided by 3. Just substitute t cube, t cube okay, this is b, tb cube. Let's erase that. Yeah, so from there you can get tb equal to 5.69 seconds. Okay, from there you can find the velocity, the acceleration of at. So use this equation. Because we know what the value is, tb. So at b, we can find at equals to 0.2 t equals to 0.2 times this value. Yeah, and we will get 1.138 meter per second square. So, yeah, so that's your AB, AT. So I'm gonna remove some of the statements here so that I can have some space to do my work. Yeah. So moving up here, yeah. So I'm taking this to be up here. I use this red color. We move to up here. Up. So when we move up here, we know that the normal velocity at B, AB, in the normal direction, ABN equals to V square, the velocity of B, over rho. Yeah, so that we have 3 point, what is the AB here? AB is given 0.2 t somewhere. I cannot remember where AB is. AB is 3, VB is 3.238. Okay, AB is 3.238. Yeah, here. Yeah, so when we substitute TB equals to 1.138, so VB equals to 0.13 square, 0.1, sorry, yeah, mistake here, not TB. So here is the case, or TB 5.69 is substitute here, and VB is 0.1 and 5.69 square. So kita dapat VB equals to 3.238 meter per second. That is the value of our VB. So then we pump this value here, 3.238 square over rho is 2 meter, and we get the ABN to be 5.242 meter per second square. So from there you can find the acceleration. Let me introduce here. So we find the velocity, so the magnitude of acceleration to be A square root of AN square plus AB tangential square. Yeah, so the answer is 5.36 meter per second square. You know, you can get the values from. You can get these values ABT from A here, and you can get the value of ABN from here. So that concludes our session for this lecture. Thank you.